Alrighty, so in this video we're going to be looking at an assessment that we've done recently on thermal and nuclear physics. So this has got everything from the AQA thermal physics section and then from the nuclear physics up to the end of the radioactive decay kind of stuff. Alright, so let's get started. So we've got essentially a decay of a protactinium, it says here, so that's the Pa particle, and it's going to decay into uranium via beta minus radiation. So we need to first of all balance this decay equation. So the first thing is, during a beta decay, it doesn't matter whether it's beta plus or minus, the nucleon number always stays the same. So that's why you've got 233 and 233. So all you do is swap a proton for a neutron or a neutron for a proton. However, in beta minus decay, what happens is a neutron turns into a proton, so the number of protons should increase by 1, which is why this is 91 over here. But if we see to start with, we have a lepton number of 0 over here. Without the additional particle, we've got a lepton number of 1, so we need an antiparticle, and it needs to be an electron type lepton. So that's your anti-electron neutrino there, and it has no charge and it has no nucleon, so it's 0, 0. Okay. Then next we're going to actually look at a different kind of decay. So these decays can all produce uranium. So there's a particle P that can undergo beta plus decay. So in beta plus decay, what happens is a proton turns into a neutron. So essentially a beta plus decay causes a movement like this on your axis, because you've got -1 protons and +1 neutrons. So this is a beta plus decay. So that puts P in this spot right about here. A alpha decay takes you down 2 neutrons and down 2 protons. So essentially it's like a -2, -2. So then Q must be +2, +2. So up here. That's how you can figure that out. Okay, so let's move on to the next question. So the final part of the first question is we've got a typical fission reaction, so a neutron being added onto a uranium nucleus, and it splits up into two what's called daughter particles. I think there's krypton and barium, I think. Well, I'm not exactly sure, but it doesn't really matter. And we've got some number of neutrons given off by this reaction. So as you should know from your particle physics section at the start, number of baryons must be the same before and after an interaction. So we've got 234 here. Currently we have, what's this, 230, which means we're missing 4 baryons. So there's 4 neutrons produced here. So you're just applying conservation of baryon number. Okay, so then we've got something undergoing alpha decay instead in this next question. So you're producing an isotope by actually adding on an alpha particle. In this case, we can see here. And again, we need to make sure baryon number is conserved. So we've got 27 and 4 giving a total of 31, which means you need 31 baryons on the side, which is why you need 1 neutron. And with these, you need to make sure you're showing these symbols as well. You don't want to be missing marks for just leaving out easy stuff. Okay, so for this to take place, obviously your alpha particle needs to get into the range of the nucleus. So this is why the strong force is problematic when you're doing the closest distance to approach method, because essentially if the alpha particle gets too close, then you get this happening, which ruins your results. So to get an alpha particle close, obviously you have to do work against the electric field that's repelling the nucleus and the alpha particle. So what you need to do is transfer kinetic energy into electric potential energy. So this is your equation for electric potential energy. We've been given the kinetic energy. So what you need to do is rearrange to make R the subject, because that's what we want, the distance. And then we plug the numbers in. If you notice, up on the previous part of the question, we knew how many protons there were in the nucleus, and we can get this value here, 2.75 times 10 to the minus 15. All right, let's move on to the next question. Alrighty, so we've got an electric heater and it's inside an insulated container. Insulated means we're not going to be losing any energy to the surroundings. And it's got 100 grams of ice in that container at minus 14 degrees centigrade. And then we're going to be supplying energy at a rate of 92 joules per second, or 98 watts effectively, and it's done for 30 seconds, by which time all the ice has reached a temperature of 0 degrees centigrade. So what we're going to do is we're going to assume it's not begun the phase change here, so we're just assuming that it's essentially gone from minus 14 to 0. So we need the specific heat capacity equation, which is this one right here. So we can work out how much energy we've supplied, because it's power times time, and it gives you this much. And then we know what the change in temperature is, we know what the mass is, so we can rearrange and solve to find specific heat capacity, 2.1 times 10 to the 3. So fairly straightforward. And then what we want to do is show the final temperature of the water if we leave the heater on for another 500 seconds. So what we need to do is we need to melt all the ice and then see how much energy is left over to raise the temperature. So this here is the amount of energy we've actually supplied during 500 seconds, so power times time. This is how much energy it takes to actually change the phase from ice to water. So then this is how much energy is left over to actually cause a temperature change. So if we rearrange specific heat capacity equation again, what we can do is we can find that the final temperature, or the temperature change, will be 38 degrees. It started at 0, so that means it's approximately 40 odd degrees there. Okay, so then if we repeat the procedure but in an uninsulated container, what that means is heat is free to transfer between the water heater system and the surroundings. So the key here is that the final temperature is 38 degrees C. We know that it's changing temperature uniformly at this stage. So we can see that it started at minus 14. So for the most of the time, the system was colder than the surroundings. And if that's the case, that means heat will be transferred from the surroundings to the ice water system, which means it's actually going to warm up faster, because essentially we're transferring more energy than we'd expect. So at the end of the time, we'd actually expect to have a higher final temperature. And it's because it spends more time below the temperature of the surroundings, so you get an extra heat transferred in. Once it gets above 25 degrees, it will then start transferring energy to the surroundings, but it's already had a massive net gain by that point. So overall, you've got a net transfer from the surroundings. Okay, and then we're going to have a look at a way of seeing what absolute zero is. So this graph you should be familiar with. So if you have a volume versus temperature graph for an ideal gas, where it intersects the x-axis is absolute zero. So that's one of the points you can plot on here. The other one they've given to you, and you should know this graph is a straight line because it's at constant pressure, which means volume and temperature are directly proportional to each other in the Kelvin scale. So that's the graph. And then in terms of calculating the number of moles, we're just using the ideal gas equation. So we've been given P and we've got V, and we know what R is, and we've got the temperature in Kelvin there, so 0 plus 273, and that gives us 9.70 times 10 to the minus 2 moles of gas. And then asks us to work out what the average kinetic energy is, so that's what this equation is for, the one you derive using the kinetic theory. So the average kinetic energy of one molecule of gas is 3/2 kT. So we've got the Boltzmann constant there, 3/2, and temperature again in Kelvin. And the data here you can see is three significant figures, so the answer should be 3 significant figures there. We want to know the total internal energy. Internal energy is the sum of all of the kinetic energies in the kinetic theory model, because we assume potential energy is 0. So we just add together all the kinetic energies. So what we need to do is multiply our answer at the top by the number of molecules. To get the number of molecules, we're going to use the number of moles times Avogadro's number. And when we do that, that ends up being 3.9 times 10 to the 2, or 390. Then we're going to look next at by explaining how the motion, in terms of motion of molecules, how a gas exerts a pressure and why the volume of the container has changed if pressure is remained constant during a temperature rise. So this is an examination of the first part of the derivation of the equation we've been using above. The kinetic energy is 3/2 kT. So if we imagine a shape, I'm not going to say it's a cube, I'm just going to say it's like a cuboid. So it's got length L and surface area on this side of A. When a gas molecule collides, so your gas molecule is going along this way, it hits the container wall and it collides elastically. So if it was going at V, it's now going at minus V. So your impulse is going to be minus mv, so impulse on the gas particle is going to be minus 2 mv. So that's the first thing that I've said here, essentially. Because we know the direction changes, we know the momentum's changed, and we can actually work out precisely what it is by modelling it as an elastic collision. And we can do that because the particle is considerably smaller in terms of mass than the container. If we use Newton's third law, then the impulse on the container, sorry, that's really messy, is going to be plus 2 mv. Why? Because if the gas particle experiences a force from the container, Newton's third law says the container experiences a force from the gas particle, or same with impulse. So that's what we get that. And the time between collisions, if we say the collisions with the container are instantaneous, is distance divided by the velocity. And all of that put together gives you this equation I've used over there, that the force experienced by the container is mv squared over L. So that's how we can get the container experiencing a force. Just move those up a little bit. And we know pressure is force over area. So that's going to be mv squared over L times by the cross section. So there's the area of the side we're looking at. So there's pressure from one gas particle on the container wall. So that's what we're doing. We're going to move into this second section here. So if you increase the temperature, you increase the kinetic energy, because we know kinetic energy is equal to 3/2 kT there. So what that's going to cause to happen is the top line of this force equation, and therefore the top line of this pressure equation, to increase. If you have more kinetic energy, you have a higher velocity. So to get the same pressure, what we're going to need to do is we're going to have to change things to compensate for it. So what we can do is we can make sure there's longer between the collisions. So what we're going to do is we're going to increase L, and what we can also do is we can increase the area over which the force is applied, and both of those things would end up increasing the volume of your container, because obviously the volume is the length times the area. So if we increase either of those two things, what we end up with is pressure being able to stay the same even though we've increased the velocity of the gas particles. And this essentially is what this question was aiming to get at. These kind of questions come up quite a bit. This is why it's so important that you know the derivation of kinetic energy, like the kinetic theory equation, like the back of your hand. This is something that comes up. And then the other thing you can sometimes be asked with this is, where are we making assumptions in this model? Okay, so that's that question. Okay, so we're going to finish off by looking at some radioactivity. So we've got some more uranium here. We've got 23892 uranium, and it's decaying into lead, which a lot of things do because lead's very stable. So it kind of comes at the end of a lot of decay chains. So what it says is we've got 8 alpha decays, and we want to know how many beta minus decays. So the first thing I've done is I've worked out what the change in the nucleon number and proton number are associated with the alpha decays. So as a result of those two, we end up with a particle or a nucleus that has 76 protons and 206 nucleons overall. So we can see we've got the right number of nucleons now, which is what we'd expect because we know beta minus decay doesn't change that. But we currently are 6 protons short, so we need 6 beta minus decays to give us 6 more protons. So that's why you have 6 beta minus decays. Okay, so then we've got we're actually going to look at how long this takes. So the uranium has a half-life of 4.5 times 10 to the 9 years, which hopefully I don't need to tell you is a very long period of time. So this is a very slow decay. And so what we're going to look at is how the components change, or how the amount of uranium changes over time and how the amount of lead changes over time. Okay, so we're going to start with 3 times 10 to the 22, and obviously after 4.5 times 10 to the 9 years, we're going to have half that. So that's what you can see here. You can see after half the time, we've now got half the number of uranium. After another half-life, we've halved it again. So that's what happens to our uranium. The total number of atoms isn't going to change, so if we add these two together all the time, we should get 3 times 10 to the 22. So that's how we know what happens to the lead so far at the various locations. So here is where their crossover is, and then we can work out this value based on 3 and that value there. Okay, so fairly straightforward. And then T seconds after the formation, there are twice as many uranium atoms as lead atoms. So we need to show how many uranium atoms there are. So if there are twice as many, what we end up doing is dividing the whole number by 3, because you've got like the 1 plus the double, so that gives you 3, and then times by 2, and that's where that value comes from. So really quite easy there. So then they want to know how long that actually takes. So it said T seconds. So the first thing we need to do is work out what the decay constant is, because we're going to be using this equation to work out time, but we need the decay constant. So we've got the half-life, so I've worked out the decay constant in years to the -1, because we want the answer T in years. So if we rearrange this equation, we now have it in this form right here. We know that n over n0 is 2/3, is 2 times 10 to the whatever, divided by 3 times 10 to the whatever. Put those numbers in and we get 2.6 times 10 to the 9 years. So fairly straightforward there. So that concludes this review of this assessment, and I hope you found that useful.